So if sigma is positive definite, so it's always positive semi-definite because it's in this case it's a vector times a vector transpose. So each term is positive semi-definite. You take the sum, you get something positive semi-definite, but it could have 0 eigenvalues. If it's strictly positive definite, that first of all is equivalent to this limiting Gaussian distribution of a density. In general, this could be degenerate, which means that you live on some subspace in the in Rn. You don't live. There's no density because you live on a say if we're in 2 dimensions, you live on a line. It comes up in control because you think of this as an input, and that controllability gradient being full rank means I can choose the input to make the state go to any other state in the state space. So there's a connection between controllability of the state space model. Can I steer from any initial state to any other state, and a density for the for this steady state law for the system, and that turns out to be a general concept even for nonlinear systems that was studied and studied and studied, which I won't talk about in this course. But there's a whole all this work by Sturken, Veridon, and Malivon, all this work on Lie algebras, because some of you have actually looked at these things, 1 or 2 of you. Instead of a controllability gradient, there are Lie algebras that have something very, very similar. And it turns out for nonlinear systems, a local notion of controllability is the same as a density. This is a whole branch of work there. That's another course. I'm just mentioning that. All right? Okay, but that is pi. So before pi was a row vector, in this case pi is a distribution and defines a steady state. Okay, for another control person, I've used U up. What happens if that's not full rank? It's actually, say we're in R2 and the thing has rank 1. It's going to have at least rank 1 because the 0th term here is just GG transpose, and we're not going to let G be 0. Okay, so it'll at least be rank 1. The opposite in a way. It's very constrained in a way, It
can only go in one direction.
Yeah, it can only go in one direction is what happens. It turns out that it's basically, so G is a vector and N's a scalar here, and I'm only allowed to push it in direction of G. Well, it turns out I'm actually stuck in that space. So if I look at, if this were G, in 2 dimensions, it turns out I'm just stuck in this line that's generated by G. If I start the origin, I'll be stuck in that line forever, And if I start outside, if it's stable, then there's deterministic behavior getting me towards the line, and the chattering in the direction of N, because the noise is pushing me back and forth in the direction of G, but then there's something, something else like this. And what actually happens is I get closer and closer to this line, but I never reach it. You can show that. So you get this really awful behavior. The fact that you have very, very different behavior. If I start here, I stay in G forever. If I start outside, I never reach it. So it's like an example of a very non-irreducible Markov chain with the intuition we've thought about before, right? So even though we have this ergodic theorem, the intuition we had for finite state space chains falls apart completely. There's no notion of reaching this line, which is where all the action is happening. And they get topologically closer and closer. So you have to think about topological notions of ergodicity, and that's why I imposed continuity right there. Right? And you can relax that. It's pretty much another course. Okay. So we need a break at this point, for sure. So, yeah. But yeah. I'll say a few more things when we come back. But let's just take 5 minutes to contemplate life. And when you come back, don't ask me questions during the break. Ask me questions when you come back, because I always get these private questions. Don't be shy. If you ever, oh, no, never mind. Ask me a shy question, and I won't tell you you asked it, and I'll answer to the entire group. How's that? Anonymous questions are allowed. So I could say that that xt was Gaussian. You know, I only used it right there. So yeah, that's a really, really good point. Well, first of all, to summarize once more, because for the one or two who just walked in, when I say has a density, I mean a density in all of our N. So in this special case, like where sigma had rank 1, it has a density, but only on this line, you know, which is the range space of sigma, if you like. Where I used the Gaussian property is in fact the sum of independent Gaussians is Gaussian, right there. That's how I got that xt was Gaussian. So you're absolutely right. So even without Gaussianity at all, we would have the same ergodic theorem. We would be able to write down that x infinity is this. You just go through the arguments I've gone through, no problem at all. And then what happens is, well, we don't know what this is. We don't know anything about this. You know, is this, if n sub n was exponentially distributed, this is a, I don't know. It's really, I mean, if this was uniform, on say, uniform on a cube, then this is, there's no word for it, you know. But it doesn't matter. So a lot of the tools in this area are designed so you don't need to know much about the processes. And I'll show you that right now. Okay? It's a perfect lead-in. So let's kill all this. Yeah, good point. I haven't defined my term. So this is often defined as ergodicity. The trouble is there are so many flavors of ergodic theorems. Ergodicity has a billion different definitions, you know. And so this is the weakest form, where you assume that the functions are bounded and continuous. You know, this is very, very weak. You know, this is convergence of distribution, is what it's called. But let's not get into that. But you know, most important in most applications, you don't want to look at bounded functions because you're looking at cost functions that blow up. So you want to relax that. You know, so. The thing is, nobody wants some incredibly complicated description of this distribution. What good is it? We might want moments. We might want, again, first and second moments, or some other cost functions, the mean of some cost function, things like that. And so it's, so we might want to bound the expectation of C of x infinity, where C of x could be, again, like the norm of x squared, or I'll just put a p there. Things like that, And in order to get bounds, we can use these Lyapunov functions. That's what we're going to find out, without knowing anything about, this crazy thing, in detail. And the key thing we're going to be looking at is this well, do I want to jump to that? I was going to do something in reverse order, but you're making me jump to this first. We're going to be looking at this Lyapunov inequality I talked about before. And this is when you all get scared to death, but I'll slow down and write down what I mean by this. So you remember we had something similar to this before for differential equations and all that. I'll explain what I mean by this. But this is fine. So for given a cost function, say, C is like a cost function, some function of the state we'd like to get a bound on, we try to find a Lyapunov function and a constant eta bar like before, satisfying this. And what we will see, so v is greater or equal to 0, we'll see that this implies that the expectation of what I called C infinity, x infinity, is less than or equal to eta bar. And this, we'll see it's trivial to prove, we're not going to do it now. It's called the comparison theorem. It's one instance of it. And I think that many of you know how we could solve this equation once you know what the hell I'm talking about with PV. PV here looks really abstract, but it's exactly the same definition we had before. Remember what PV was? I don't need any of this anymore. So I had a matrix vector multiplication for this, but I also had a probabilistic interpretation. If you go back in your notes just half an hour ago, PV, V is a function, PV is a new function, and it's defined as a conditional expectation. So I'll put the brackets around it just like I did before. I take the function v, I hit it by this, what I'm calling p, and I validate x for Markov chain. What I mean is, I see nods, that's good. It's the expectation of v of xt plus 1 given xt equals x. That's it. So that's just a definition. All right, so we have a mapping from functions to functions. And let's go through an example. So let's do it. So I want to get a bound I want to bound the expectation of C of x infinity. Well, that's the steady state, okay? I haven't given you any theory yet, but I claim that if I have this bound, I'll have this bound. You'll see it's a one-liner. It's like the fundamental theorem of calculus. It's that simple. It's just like what we did before. So I want to say that's less than or equal to something. All right. So what am I going to use for V? Somebody who took state space control? Because it's exactly like what you use for stability theory. Well, yeah, I almost, what, say it again? XT?
Some matrix.
Yeah, I mean, yeah, exactly. Okay, so Q can just be positive semi-definite. That's no problem, because I don't need this to be strictly positive everywhere. But I want my Lyapunov function V to be positive everywhere. I want it to be, usually I want that. Not always. I mean, sometimes, well, anyway, we'll get back to that later. And let's just try it out. So we know how to do this. We know how to do this. I can't do this in general for any Markov chain, but I was sticking to this linear system. Right. And and just for the hell of it, again, let's assume that the expectation of NT is 0. And the expectation of NT squared equals 1, but not Gaussian. So it could be like a two-sided exponential, and if we're or it could be uniform on the appropriate width or something. All right, so given x equals x, that's independent of xt. It's just an expectation. Okay, so that and that are the same thing. So it'll never be any harder than that. The only thing hard here is to memorize this notation. You're going to be forced to do that. You're going to be forced to memorize that notation. Because again, my hands are tied if you refuse to learn it. And 1 or 2 if you will, and you'll bomb in the course. So just make flashcards. I swear there's only like 2 or 3 things I'm going to force you to memorize. All right, there it is, the definition. Okay, flashcard for that. All right, it's experience. It's like the one thing, a certain percentage you always refuse to learn, and it slows me down. Okay, so your homework. So plug it in. Okay, so V, I just plug in X. That whole thing is my X. I'm plugging in that vector, substitute it in there, right? All right, and then I get a whole bunch of nasty terms. I'm going to get the term that's quadratic in X here. I'm going to get the cross terms, this and m times that. But remember the mean of m, and I'm assuming to be 0. So those cross terms vanish.
Should be a transpose there. Right?
And there should be a transpose there. Just testing you, Jonathan. Is that it? That's simple, huh? Okay, and the next thing you do is again, it's this faith-based analysis as well, is I want PV to be less than or equal to V, so I need to stick a V on the right-hand side. So what I've done here is I've sneakily stuck in V, All right, but then I've subtracted it off because I got a minus x transpose mx there. So those guys cancel out. The minus minus becomes plus. So these are indeed the same thing. All right, and so what's the equation I have to solve now to get my Lyapunov thing? The Lyapunov equation is this equals q. Okay, so that's something you learn in a control course, that thing is equal to q. Okay, so there's a layup command in MATLAB. Okay, somebody gives you q, they tell you, this cost function is really important. You know, if I can get a bound on this, you know, that's I know how to set my options strategy for, you know, to beat Wall Street. All right, and you say, well, I've got a trick for you. You type layup in MATLAB, you give it q and f, and it delivers m. And then once you have m, you get eta bar. So once you solve the Lyapunov equation, you don't get an inequality, you get an equality, and eta bar again is equal to this term right there. All right, so this is what's nice about this, is you don't have to know a lot about the statistics at all. Give me first and second moments for the Markov chain. Apply the same tricks you'd use for deterministic analysis. This is exactly what you use for stability or performance analysis for deterministic systems. And and it turns out you don't get an inequality, you get an equality. Okay, so it's actually exact. All right? So that answers your question. We don't need Gaussianity. we need to know first and second moments, and then we can get second moments. All right. Yeah. Right there. Yeah. That's what we will see. So if I can find a solution to this inequality for a function v which is greater or equal to 0, I'm automatically get a bound in the steady state. And I'll make this precise. This was a special case where I could identify this x infinity. We'll make that precise later on.
GAS or something?
What's that?
Yes.
No, nothing to do with that. Because those notions, GAS is global asymptotic stability. That's reserved for deterministic systems. But I mean, it is similar. What have we shown? We've shown that you know, this is true. I mean, you can work it out by hand. In the case where C is quadratic, it's not hard just to work it all out and show this is true. You know, we don't need C bounded. I mean, this quadratic case, it's pretty trivial. But this is like global asymptotic stability, but it's the distributions that are converging. You know, it's the distributions that are globally asymptotically stable, and the distributions evolve as a linear system. That's the thing. So even though we had I mean, this is linear, but I mean, if a Markov chain driven by nonlinear dynamics, the distributions evolve as this p to the t.
In the math that we were doing for PV equals all of those lines, when did the excitation operator kind of disappear?
Oh, where?
Like PV equals.
Well, let's go through it. Yeah, let's go through it. So we had this. This is definition. Then we have this. But now all I did is I I didn't want to waste our time just saying that this has a quadratic term as an n1 times n1. And we said that's equal to 1. And there are cross terms, but the mean of n1 is 0. So it's right there.
Okay.
It's when we just expanded this out, we only ended up with 2 non-zero terms. Because the expectation of the cross terms was 0. Yeah. Yeah.
Yeah, I mean, I suppose for like the terms that solely like have deterministic values, the expected values, like
You can just take them out of the expectation.
What's that?
yeah, the deterministic values are effectively coming out of the expectation, or
I'm not sure I understand.
And then there are others with just one and one.
Yeah, there were,
Oh, that's what you're saying. right.
yeah, the fx
Right.
squared basically was just
Yeah.
nothing.
yeah, this is the first term. These, yeah, there were 4 terms, and I just didn't want to waste the chalk. I threw away the cross terms.
Yeah,
Yeah.
F, M, G, and X are all deterministic.
Yeah. Yep, these are all just matrices. That's right. Okay, I don't want to leave this yet. You can do spectral theory here as well. So, even though this is not a matrix, you can still talk about eigenfunctions, eigenvectors, but they're functions. And they still have meaning, it turns out. And just to keep playing with this a little bit longer, let's do it. Am I allowed to erase this? Anybody have a guess what lambda will be here? And remember, before for finite states Markov chain, it had to do with the rate of convergence to stationarity. And we already saw that, remember, xt was equal to f to the t x0 plus a summation of something where I made a bunch of typos and you corrected me. But there was this transient term here, right? So we know the rate of convergence to stationarity has something to do with how fast f goes to 0. And how fast is that?
Largest magnitude eigenvalue that is not 1.
Well, no, f is stable. All the eigenvalues are strictly within that circle. So the eigenvalue maximum, yeah. So somehow the spectrum of the Markov chain should have something to do with the spectrum of f as well. But it's got to be much bigger, because for a Markov chain with m states, we had m eigenvalues. And here, we don't have m states, it's Rn. It's uncountably infinite. So there's got to be a lot of you'd expect a lot of eigenvalues. But let's test that intuition, And V now is a function, though. Remember, this is, when we're talking about a Markov chain Rn, this is no longer a vector, but a function. And this is a conditional expectation. But you can imagine it's going to be pretty simple. And so what's the simplest function you can think of? Yeah, well, V could be constant. That's easy. Then this is 1. So if V of x is identically equal to 1, so the 3 lines mean it's 1 for all x, and lambda equals 1, then check. Yep, that's true. Because the conditional expectation of a constant is the same constant. What about V of x linear? That's a xi, I guess, if you're Greek. Correct me. Let's try a linear function just because so we can make it easy on ourselves. And also because you can kind of hope that C might have to do with an eigenvector itself. So C is an n-dimensional vector. And we want to somehow slip in a vector, so we can, where's my, want to slip in a vector so we can test our hypothesis about the spectrum of F compared to the spectrum of the Markov chain. All right. And that shouldn't be very hard. Because do exactly the same thing as before. Fx plus Gn. All right. No difference, right? I just put a little v here instead of the grand big V there. All right? But then now this is a linear function instead of a quadratic function. What's that? Yeah, I think I heard somebody say it. So I've got the, again, this is X is just a vector. F is a matrix which is fixed. That's just a vector, nothing random there. I've got the expectation of a linear function of n1, and somewhere I said its mean is 0. Okay, so it just turns out to be equal to C transpose Fx. And we want that to be equal to, put a question mark there, lambda v of x. You know, we want PV evaluated x to just be a scaled version of v of x for all x. Okay. So I'll put a question mark again. Is that equal to a constant times C transpose X? Remember, F is an n by n matrix. All right, this is pure linear systems theory. I just took a guess that maybe a solution to this eigenvector equation was a linear function of x. Okay, and then I went through this, and I said, well, if it's going to be true, then this has to be equal to this for all x. And if this is a row vector, and that's a row vector, and if the dot product with every value of x is the same, they have to be the same.
So I'm not sure I quite understand. How is the eigenvector is a function of x?
Now remember when we go to, so I made a big jump here. I said that there was a connection between functions and vectors, back and forth. But here I'm just sticking to functions, you know. And so when I said PV for finite state space chains, I meant a conditional expectation. I mean it now too. And so V will be a function of the state space. Whether it's a finite state space or a general state space, V will be a function of the state space. And PV will always mean that.
Okay, and
Yeah.
P here is not representing any kind of matrix. That's just part of
Yeah, that's the thing. It's no longer, so that's the thing is it's no longer, you know, you only had a very crisp matrix interpretation in the finite state space case. For a finite state space case, P was an n by n matrix, but now it's a conditional expectation. Yeah, that's an operator. Yeah, just like the weird differential generator business. Yeah, but this is what I mean about some, you know, there's just a few bits of, you know, of language like this you need to
The thing though is that, like,
yeah.
when we started with the finite state space, you kind of arrived at P through like, I guess, abuse of the simplicity of the finite state space and got its matrix representation and interpretation, and then you kind of just told us that it's also equal to this expected value.
No, I did. I proved it. So I said, here's the definition of Markov chain. How would you compute this? Oh, it's a matrix multiplication. We interpret V as a vector, and we get a, you know. And so now I'm saying, well, let's just take that as a definition from now on. Yeah. And it's completely consistent. Yeah, completely consistent. And it's just useful compact notation. You know, having to write this out all the time is just tedious as hell. You know. And especially when we're talking about things that are really just like finite dimensional objects. Right? And so you see what we find is that C is a left eigenvector of F. So if I transpose this, I get F transpose Xc equals lambda Xc. There we go. That's what you find out here. Because Xc transpose F equals lambda Xc transpose. Just take transpose of both sides, and you'll get this equation. Okay. So the left eigenvectors of Xc give you eigen functions of this. They're invading already? Yeah. Or no? Yeah. You can come in. Now that can't be it, because that would there's only n solutions. And it turns out there's lots more. So if I got polynomial functions, quadratic functions of x, I could give you more solutions, and some cubics, more and more and more. And there's a whole lot of eigenvalues. But the dominant one is this. Okay, so just what you said. Take the eigenvalue that's closest to the unit circle, and then take the eigenvalue that's closest to the unit circle, solve for this eigenvector equation, and we will get the dominant term there. And so that does work. And it turns out there's a lot of meaning with these eigenvectors, which maybe we'll be able to touch on later on. It's another topic in a way, but it turns out that just like pi, that left eigenvector, which was a steady state distribution, has a lot of meaning. The dominant eigenfunction corresponding to the lambda, which is closest to the unit circle, has a lot of meaning too. And it's very hot in computer science. People talk about metastability, and in physics as well. And but there's no time to talk about that now. So maybe I'll cook up an example that's tractable for either homework or lecture. Okay. Cool. So no energy for more examples. I think this is a good place to stop. So I'm going to, basically what I'm doing is I'm getting into these sort of fixed point equations, because these will be our dynamic programming equations, something very, very similar when we get to optimization. And we've already seen we can get performance bounds if we can solve these Lyapunov inequalities. We can also get approximately optimal control policies when we get to control. And so we need this compact notation to be able to move through that material. So please learn it, please. Let me tell you, and you. Until next time.